Next, let's talk about this basic but remarkable theorem about interpolation for fractional linear transformations, which is a three-point interpolation theorem. It says that for each distinct a, b, and c in CP1, and notice here I'm writing a, b, and c as points in CP1, which might be different than I've been doing it. So here a will be thought of as a1, a2 inside of CP1, and similarly for b and c. So we have distinct a, b, and c in CP1 and distinct alpha, beta, gamma in CP1. Then there exists a unique fractional linear transformation F that sends A to alpha, B to beta, C to gamma. Now we can prove this pretty easily through two lemmas. The first lemma is how we will address uniqueness. So it just says if we have a fractional linear transformation that sends 0 to 0, 1 to 1, and infinity to infinity, and what I mean here by 0 is the point that we identify with 0 in CP1. So we're sending 0, 1 to 0, 1, and 1 is 1, 1, and infinity is 1, 0. So if we have a fractional linear transformation that fixes these 3 points, then it has to be the identity map. And we can just show this pretty directly. So we take such a fractional linear transformation and see what it means for it to fix these 3 points. So if it sends 0, 1 to 0, 1, that means 0, 1 is equal to the second column of our matrix inside of CP1. So this just implies that B is 0 and D is non-zero. The next requirement, that infinity goes to infinity, says that our first column, AC, is equal to 1, 0, which again we can use to imply that C is 0. And now the point identified with 1 in the plane, 1, 1, maps to itself. And since we already know B and C are 0, this has to map to AD. And this implies that A equals D, and they have to be non-zero. So what does it say about our original matrix? Well, it's equal to A0, 0A. But inside PSL2C is just the identity matrix. And so this implies that F is the identity. Okay, so this lemma will be how we'll address uniqueness. And then the next lemma will be how we will address existence. So it says, given distinct A, B, and C in CP1, there exists a fractional linear transformation F that sends 0 to A, 1 to B, and infinity to C, using the same notations as before. And this we again do in just a straightforward way and try to construct the matrix explicitly. So how does this work? Well, since these points A and C are different, that means the corresponding vectors are not multiples of each other, so they're linearly independent, so they span C2. That means we can write our third vector as a combination of them, so I can write it as lambda 1, A1, A2, plus lambda 2, C1, C2, for lambda 1, lambda 2, and they have to both be non-zero, because if one of them were 0, then A or C would be equal to B inside of CP1. So now that we do this, we can build the correct matrix in PSL2C that does what we want. So we need, recall, we need infinity, which we write as 1, 0, to map to C. And so a first guess might be that we would put C in the first column, and we need 0, which we write as 0, 1. We need that to map to A. So we might want to put that in the second column. But we also need 1 to map to B. And this matrix that as we've written it, may not do that. But if we throw these lambdas in there, it actually does the right thing, because you need this column plus this column to add up to B. Well, replacing A and C with multiples doesn't change them inside of CP1, so that's not a problem. So I can put lambda 1 here, lambda 1 here, lambda 2 here, and lambda 2 here, and this matrix works. And you can just check that the corresponding FA maps 0 to this lambda 1 times A, but that's the same as A in CP1, and it maps infinity to lambda 2 times C, which is the same as C inside of CP1, and it maps 1 to what you get when you add these two together, which we've rigged to be B, and that's what we want. So with these two lemmas in place, it's pretty easy to prove the main theorem. Recall what was the main theorem? We have 3 distinct points, A, B, C, and 3 other distinct points, alpha, beta, gamma, and we want to show there's a unique fractional linear transformation that interpolates them. So the proof based on these two lemmas is pretty easy. Okay, so we build one F that sends 0, 1, infinity to A, B, and C, and you build a G, a fractional linear transformation that sends 0, 1, infinity to alpha, beta, gamma. Then F inverse G will interpolate, because F inverse will send A to 0, B to 1, C to infinity, and then G will send those to alpha, beta, gamma, and it does the right thing. So that's all using the second lemma. Now for uniqueness, if I have another fractional linear transformation that does this interpolation, well, what can I say about this fractional linear transformation? So I've rigged this here so that F composed with H composed with G inverse. Well, what does it do? It sends 0. Well, F sends 0 to A, and H is assumed to send A to alpha, and then G inverse will send alpha to 0. And then this is rigged exactly to send 1 to 1 and infinity to infinity. And now we can invoke the first lemma, which then says that this has to be the identity map. And then you compose on the left with G and on the right with F inverse to get that H has to be the function that we already constructed. So that proves uniqueness. One final thing to point out about this proof and the theorem is that it's completely constructive, obviously. If you want to do this interpolation with concrete points A, B, and C, and alpha, beta, gamma, you can just follow this procedure and build F and G as we've done it. So you build F as in the proof of the second lemma. So you just take A and C and write B as a linear combination of them using techniques from matrix algebra. And that's how you can build capital F. And you do the same thing to build capital G here, and then you just invert F and compose with G, and then you get your solution.